Last lecture, we covered the following. We looked at a definition for isomers and isomerism. You will recall that isomers are compounds with the same molecular formula, but we have two types in general, or two broad categories. And one is structural isomer or constitutional isomer, and the other broad category is stereoisomer. So it is important in terms of how we represent stereoisomers in organic chemistry, because as you know, looking at molecules in three-dimensional space requires a lot of perception. So here are three representations that we looked at. The first was the dashed wedge. And just as a review, remember the dash is representing the groups that are in the back, and the wedge are the ones that are in front. We next looked at the Fisher projection, which is essentially a cross, where the horizontal here represents the groups that are pointing towards the reader, and the groups that are in the back, the vertical, are the groups that are in the back. Another representation that we looked at was the Newman. And of course, here we'll have at least two carbons. So we'll look down one carbon, and essentially what you see is something like this, where we have an atom here, an atom here, and an atom here, looking down this carbon, and you can't see the back carbon, so we put a circle, and then what you will see off the back carbons will be these groups, and that is the Newman representation. We then emphasize or get a little more specific in terms of stereoisomers, and we defined that there are two kinds, or we looked at two kinds last lecture, and those were enantiomers, which are mirror images of each other that are not superimposable on each other. And we also looked at diastereomers, which are not mirror images of each other, and they are not superimposable. And lastly, we looked at a way of naming optically active or stereoisomers that are enantiomers or diastereomers, and that's the R and S configuration. In today's presentation, we'll cover the following. We'll look at symmetry elements. As we'll see, these are elements that are very helpful in determining if a molecule is optically active or not. We'll apply those elements to symmetric molecules, and the one in particular will be the Meso compound. So we'll discuss that. We'll apply the symmetry elements to asymmetric molecules or asymmetric compounds. Some examples that we look at will include amines, allenes, adamantanes, and spiral compounds. So we'll examine those to see if they are, what type stereoisomers they are, using the symmetry elements that we'll define in a second. Then we look at atropisomers. So atropisomers are isomers that result from restricted rotation, typically about a carbon-carbon bond. We'll emphasize more about that in a second. Then we'll look at the properties of asymmetric compounds and how we separate asymmetric compounds or how would we separate chiral compounds. And lastly, we'll look at stereotopicity, which is basically the analysis of stereoisomers. And we'll look at some terms here. The first term is homotopic, enantiotopic, prochiral, and diastereotopic. You'll see that these are very important tools that are used to analyze compounds that look very similar but are slightly different, and the NMR spectroscopy can detect these differences and sometimes complicates the NMR spectrum. So let's start. Symmetry elements. So we look at 4 symmetry elements here. And of course, one is reflection in a plane of symmetry. So we have a plane or a flat surface. Is there a reflection across that plane? And what is that reflection? We'll see later on if that reflection is the same, then that molecule is described as symmetric. Inversion of atoms through the center of symmetry. So in other words, here you have a molecule and you'll determine what is the center of that molecule and see if there is an inversion going from one end to the other end, and determine if the groups are the same or not. Rotation about a proper axis. So in other words, if you have a molecule and you find an axis, a line right through it, through the center, if you rotate it by 180 degrees, such as also known as a C2 axis rotation, what results? If the result is the same, then that molecule is described as symmetric, and of course if it's different, it's asymmetric. The last one we look at is rotation about an improper axis. Basically what this involves is rotation about an axis followed by a reflection, or in other words, carrying out any 2 of these 3 operations, and that's called an improper rotation. So as we described earlier, these symmetry elements are helpful in determining chirality, and you'll see later on that another term that's used for chirality is also optical activity. Let us start by looking at these compounds here. These are compounds with 2 chiral carbons. So here are the chiral carbons. And just to remind you, a chiral carbon is a carbon that has 4 different groups bonded to that carbon. We can assign R and S based on the priority assignment. Just to review, we have, looking at this carbon here, we have bromine attached to that carbon, this group attached to that carbon, we have a methyl group attached to that carbon, and a hydrogen. If you were to assign priorities, this bromine has the highest priority based on atomic number, followed by this carbon. Why this carbon? Because it is bonded to bromine and another methyl. So that's priority number 2. This is priority number 3 because it's a carbon, and this is priority number 4 because it's hydrogen. Since this is the Fisher projection, the atom of lowest priority is in front because it's in the horizontal. So in going from BR 1, 2, and 3, you'll see that that's an R, but since this group is in front, it's an S. So by now you should be pretty comfortable in assigning R and S configuration to a stereogenic carbon. Getting back to our discussion though, in terms of symmetry, look at these 2 molecules here. You will see that they are in fact mirror images of each other. If you draw a mirror right down the middle here, you will see that they reflect on each other. So therefore they are enantiomers. Notice again, we know that they are enantiomers because this is S and that's R, so it's opposite. This is S and that's R, so it's opposite. Looking over here, for example, here is it. We could do the same analysis. Put a mirror right down the middle. This is a chiral center, S and R and S. So this is the mirror image, but are they enantiomers or not? We'll have to do an analysis to make that determination. So let's look further. Looking at the same two molecules to the right, there is a plane of symmetry right across the center here, where this half reflects on that half. So in other words, this molecule is symmetric, pardon me. This molecule is symmetric because there is a plane right down the middle here, and this half reflects on that half. Same here. This half, its mirror image, this half reflects on this half. So therefore, it is a symmetric molecule. Another test is that these two molecules are superimposable on itself. So if you take this molecule, it is superimposable on that molecule. Therefore, they are the same molecules. They are the same molecules. They are not enantiomers, and they are not diastereomers. Okay, they are described as meso compounds. A meso compound here is one that has chiral carbons, but its mirror image is the same. Or we could put it differently. If there's a plane of symmetry, they are the same molecules, and in this case they are described as symmetric molecules. Let's look at some more examples here. Here is cis-1,2-dimethylcyclopropane. There's a plane of symmetry right here, right through the center here. So just imagine a plane going right through that molecule. You can see that there's a reflection of one half on the other half. So therefore, this compound here has a plane of symmetry. Its mirror image will be the same as this molecule. So therefore, that's described as a meso compound. The trans, on the other hand, if you should put a plane right down here, you will see that this half does not reflect on the other half. So therefore, this molecule is described as asymmetric, since it does not have a plane of symmetry, and its mirror image will not be superimposable on itself. So therefore, this is not a meso compound. Let's look at a couple more examples here. These are mirror images of each other, but notice here that the groups are different. So we have a chiral center here, a chiral center here. So the mirror image would be S and R and S and R. But notice again that there is not a plane of symmetry as we have seen before for the meso compound, because this half does not reflect on that half. Same here, this half does not reflect on that half. So therefore, this is in fact asymmetric molecule, and they are enantiomers. So just to refresh your memory, enantiomers are mirror images of each other that are not superimposable. So these are mirror images of each other, and they are not superimposable. We can add another criterion here, in that they do not have a plane of symmetry. So in other words, asymmetric compounds or enantiomers, they do not have a plane of symmetry. They are mirror images of each other, and they are non-superimposable on each other. As we said last lecture, it's important to determine enantiomers because of the activities of different activities of enantiomers in the biological system. Another example here is, of course, we have now R and R and R and S. So these are not mirror images of each other. And there is not a plane of symmetry right through here. As you can see, they do not reflect on each other. Same here. They do not reflect on each other. Some atoms do, but at least once you have a difference, it is considered as asymmetric. So in this case, as you know, these are now diastereomers. So diastereomers here are molecules that contain chiral centers. They are not mirror images of each other, but they are non-superimposable on each other. So therefore these are described as diastereomers. Notice again, lack of plane of symmetry. So we can again add another criterion to diastereomers. They are not mirror images of each other. They contain chiral centers, and they do not possess a plane of symmetry. Let us look at a very simple molecule here, or two simple molecules here that we looked at last lecture. As you can see here, this carbon here has 4 different groups bonded to it: the red, green, yellow, and white. Let's see if there is a plane of symmetry. So if you have a plane right down here, this reflects on that, but they are different. Even if you have another plane going right through here, this reflects on that, then they are different. So you can try and draw different planes through either of these molecules, and what you will discover is that it does not have a plane of symmetry. It's described as asymmetric, and they are in fact mirror images of each other, and they are enantiomers. So as we said last lecture, we can use these criterion to determine enantiomers, mirror images of each other. So just imagine a mirror right down here, mirror images of each other. They are non-superimposable, and now we can say that they lack a plane of symmetry. So another term that we use is they are also asymmetric molecules. Let us look at a last criterion here. That's the SN axis of element of symmetry. What this involves is basically 2 operations. So let's look at this molecule. It has chiral carbons here, here, and here, and the question is, if you carry out some activities or symmetric elements on this molecule here, if you get back the same molecule, then it has that symmetry element in it. So here we have a 180-degree vertical rotation. So rotate this, you get this. And then we have a horizontal reflection. So reflect across from each other here, and what you'll get is this. Notice that this molecule is the same as that. So we have in fact carried out a symmetry element here, the SN, and we get the same molecule, so therefore that molecule would be symmetric. Okay, let's look at enantiomerism due to asymmetry. As we said, if there are 4 groups bonded to a carbon, it's chiral, and it's asymmetric because no matter how you draw your planes through that molecule, they will not reflect on the other half. 4 different groups. However, looking at a tertiary amine, here is a pair of electrons and it has 3 different groups bonded to it. The question now becomes, could an amine be optically active? And yes, it can be, because we can treat this as a group in itself, so therefore that would be the 4th group. So now we have 3 groups here, alkyl groups, and a pair of electrons here. The problem is, as we'll see, it's hard to isolate one enantiomer over the other enantiomer because, as you know, there's rapid inversion of this here. Let me get rid of this. Because there is rapid inversion as we across the amine here, the tertiary amine. But if these groups are large enough, we can in fact slow down the inversion and isolate it. Let's look at a more specific example here. Here is an amine. It's a cyclic amine known as the aziridine molecule. Here there is possible to have rapid inversion, but of course it's more difficult because of the cyclic structure that's a part of the amine here. But as you can see, it has 1, 2, 3 groups bonded to it, different groups, and a pair of electrons here. So there is an equilibrium where there's rapid inversion, but because there is a 25 kilocalorie per mole barrier, it's possible to isolate these as enantiomers, typically at low temperatures. So these molecules are in fact optically active, or another term for that is they are in fact asymmetric. Let's look at these. Here is an allene. So this is a double bond and another double bond right next to it. So as you know, a double bond here is flat, but if you put another double bond next to it, it will go perpendicular or orthogonal to that double bond. So we'd have these atoms here in the plane, and these would be sticking opposite or perpendicular to that plane. So this is a optically active molecule. The term that we use here is disymmetric. The key here is that you can find an element of symmetry in these molecules, but the bottom line is they are non-superimposable mirror images. So that will determine if they are in fact symmetric, asymmetric or symmetric. So we use the term disymmetric because there's one element of symmetry that you can find here, but the bottom line is their mirror images are non-superimposable on each other. Here's another type, the spiral compound. Remember, the spiral compound involves two cyclic rings that are fused at an intersection such as right here. You can in fact find a element of symmetry here, but the same thing applies, that their mirror images are non-superimposable on each other. Another one here is the adamantane, which is basically a bicyclic type system, very rigid bicyclic system, does not flip as the cyclohexane ring could, but it has this conformation here, and you can in fact see an element of symmetry where groups can reflect on each other, but the bottom line is they are non-superimposable mirror images of each other, and they are described as disymmetric molecules. Let's look at another concept here, and this is one that's called atrope isomer. An atrope isomer. Let's see if you can visualize this one, because it's a little tricky to see because it's drawn on two-dimensional paper or screen in this case. But just imagine this bond here, and it can rotate. So if you imagine this being in the plane of the paper or flat on the screen, if this rotates to give it a orthogonal or 90-degree angle, this would be sticking up and behind the plane of the screen, that is called an isomer. Again, it's disymmetric because you can find a plane of symmetry, but it's disymmetric because its mirror image will be different from this, or they are non-superimposable mirror images. Okay, let's look at properties of chiral compound. It's really property, because chiral molecules or enantiomers are essentially the same. All the properties are essentially the same except one. You may recall from your organic, one of the main ways we can determine two unknowns is by comparing the properties of these two unknowns. If they are different, more than likely, they are different compounds. I shouldn't even say more than likely. If they are different, they are different compounds. But if all the properties such as melting points and color and all the other physical properties are the same, it's very difficult to determine if these two compounds are the same or not. For enantiomers, the only difference between the properties of enantiomers is the direction in which it rotates polarized light. You will recall from your organic course, polarized light is light in which all the vibrations are filtered out, so it's coming in one direction. And if the molecule is chiral, it rotates it either to the right or to the left. Its enantiomer would rotate it in the opposite direction. So here's glyceraldehyde. As you can see, it's chiral because it has 4 different groups bonded to it. So therefore, polarized light that's coming in, it will rotate it to the right or to the left. This particular one will rotate it to the right, and it's designed by a plus. As you can see here, plus 8.7. There's also a D that you'll see in some books for some of these stereogenic molecules, and that's because it rotates it to the right, so it's called dextrorotatory, hence the D. Its enantiomer, which is also chiral, mirror image, will rotate the plane to the left, negative, same degree as we had here, but in the opposite direction, and we assign an L here because experimentally we observe that it goes to the left, so we call it levorotatory. So that was an old experiment that was done years ago and on glyceraldehyde, and hence we have the L and D. Notice again that the R and S assignment that we did for these chiral carbons do not necessarily relate to the D and L or plus or negative. The R and S are absolute assignments. Absolute assignments. These are experimental assignments. Experimental. So they may not necessarily coincide with each other. Another experiment that's typically done on stereogenic molecules. Notice we can also now use the term optically active molecules, because now we know that enantiomers will rotate the plane of polarized light or interact to the right or to the left. So we say they are optically active just because of that interaction. So this is called optical rotary dispersion, ORD. And here's a typical experiment. We have a molecule here that's optically active. In this type of experiment here, the optical activity is determined over a region in the UV spectrum, typically in the near UV spectrum. So we go from this wavelength over to here, and we monitor the optical activity, and we get a curve like this. You will see in the book such as the Cotton effect, positive Cotton effect and negative Cotton effect, if there is a maximum and a minimum, to use that. But anyhow, bottom line is, because enantiomers interact with polarized light, we use the term optically active. That's a special property just for enantiomers. That's the only property, I should say, not even a special. That's the only property that's different between enantiomers. And as a result, we can study enantiomers using its optical activities. Let's look at how we separate them. So as you can imagine, in the lab, if you make a optically active molecule, such as the ones shown here, these are enantiomers of each other. It's carboxylic acid. So you can imagine you go in the lab and you make these two compounds, and they are actually in the same vessel. How would you separate them? And one technique that can be used is to carry out a reaction with another optically active molecule, such as this one, an alcohol. As you know, an alcohol reacts with an acid to form an ester. But the bottom line here is that now we have a diastereomer here and a diastereomer here in the same reaction vessel. Since diastereomers are different, they also have different properties. Typically, sometimes melting points and polarities and so on are all different compared to enantiomers. Now we can carry out the separation by a physical method, typically by chromatography, to get A, container A, and container B with the two enantiomers. What's needed next, of course, is to convert the enantiomers back to the carboxylic acids, which is easily done by hydrolysis. So if you heat this up here in an acid, H3O plus, and heat, you get your acids back and your alcohol here in two separate containers, pure enantiomers. As you can imagine, in the pharmaceutical industry and in the research lab, there are other techniques for separating out enantiomers, and one that's typically used is chiral columns. So you purchase a column that's chiral, and the enantiomers here they combine with, through different type interactions with the chiral species in the column, and it's separated based on that interaction, and that's known as chiral HPLC. That's routinely done in the research labs for the separation of enantiomers. Lastly, let's look at another topic here, and it's stereotopicity. This is important, as we'll see later on, whenever we start analyzing NMR, nuclear magnetic spectroscopy, of molecules that have hydrogens that seem to be equivalent. So let's look at the first definition here: homotopic hydrogens. Homotopic, as you can imagine, homo means the same. So if you have a molecule like this, we're looking at this hydrogen compared to this. Since all three are equivalent H1s, we are comparing H1s to H2s. So if you replace here H1 with an X, you get this. And if you replace here H2 with an X, you get this. It turns out that these two molecules here are in fact identical. So these hydrogens here are called homotopic, identical atoms that occupy identical or equivalent environments. Notice the key word here, equivalent environments, because as you know, for the NMR can detect hydrogens that are in environments that are not equivalent. Another term is enantiotopic. As you can imagine, it has to deal with the enantiomers. So here's an example. Here's a molecule. This is not chiral because it has 2 hydrogens bonded to the carbon. It does not have 4 different groups bonded to that carbon. If you replace HA with X, you get that. If you replace HB with X, you get this. As you can see here, these are enantiomers. So these are enantiotopic hydrogens. Enantiotopic hydrogens because the replacement gives enantiomer, not the same molecule. Now let's look at another example here, starting with butane, for example. The question is these 2 hydrogens here. You replace this with deuterium, you get this. It is the enantiomer. You place this H with deuterium, you get this. It's the enantiomer of this. Notice this is R and this is S. So these 2 hydrogens here are enantiotopic, and we describe the molecule here as prochiral. So the molecule here, butane, which has is prochiral, even though it's achiral. But if substitution of the hydrogen gives you the enantiomer, then it's described as a prochiral hydrogen here and a prochiral hydrogen here. Let's look at another example here, diastereotopic hydrogens. So here we have, let's look at this for example, 2-butanol. We have 2 chiral carbons here. Why chiral? Because we have 1 chiral carbon, one chiral carbon here because we have 1, 2, 3, and 4 groups bonded to this carbon. This carbon here is not chiral because it has 2 hydrogens bonded to that same carbon. However, the replacement of HA with X gives this, and the replacement of HB with X gives this. This is now chiral. This is now chiral. This was chiral from before, still is. This was chiral from before, still is. So these are called diastereomers. So therefore, these are called diastereotopic hydrogens here. Diastereotopic hydrogens. In the NMR, these hydrogens, because they are in different environments, to give diastereomers, if substituted, they will split each other in the NMR. So again, even though they look very equivalent here, but they are really not, because they are in different environments and the NMR can detect that. Here's another example. These 2 hydrogens, these 2 methylene hydrogen diastereotopic, will split each other in the NMR, and these are homotopic. Why? As you can imagine, this hydrogen here will be on the same side as these, and this is in the back. So if you, which makes these 2 hydrogens in a different environment. Over here, this is on top, but it sees this on top and that on the bottom. This is on the bottom, but it sees that on the bottom and that's on the top. So you can see that these 2 here are equivalent and described as homotopic and will not split each other in the NMR signal spectrum, whereas this one here, they are in different environments and they are called diastereotopic and will in fact split each other in the NMR spectrum. Okay, so summary. Let us just summarize by looking at the different terms before we quit. So, a chiral carbon, also known as a stereogenic carbon, is a carbon that has 4 different groups bonded to that carbon. 4 different. Okay? Enantiomer, non-superimposable stereoisomers that are mirror images of each other. We can even go further and saying that they are now asymmetric. They're not symmetric. Asymmetric molecules, molecules that do not have a symmetry element or plane of symmetry. Symmetric molecules, they do. They're called achiral, or one example is, of course, the Meso compound. Optically active molecules are molecules that rotate the plane of polarized light. They are typically, or they are, in fact, enantiomers. If it rotates to the right, it's dextro-rotatory, to the left, levo-rotatory, or positive and negative. Again, remember that these are experimentally determined, whereas the R and the S, the absolute configuration, are absolute assignments. Diastereomers, asymmetric stereoisomers that have more than one chiral atoms and are not mirror images of each other, and they are not enantiomers. We can add another term. They do not have a plane of symmetry. Meso compounds, compounds that have chiral centers, but they are optically inactive. All right? They are optically inactive. In other words, the mirror image of a meso compound is the same as a compound. Homotopic groups are identical atoms that occupy identical environments. As we saw, that in this case, the NMR will recognize that. Enantiotopic, identical atoms that occupy non-equivalent environments because they give enantiomers, and substitution of one hydrogen or one group for another results in enantiomers. Prochiral, structures that are chiral, achiral, but can be made chiral by substitution. So they are achiral, typically because they have two of the same groups bonded to the same carbon, but substitution of one for another group gives the enantiomer, and the other one gives the other enantiomer. Diastereotopic, identical hydrogens, for example, identical atoms that occupy a non-equivalent environment, and substitution results in diastereomers. And remember, in this case, since they result in diastereomers, which are different compounds here with different properties and so on, the NMR can detect diastereotopic hydrogens, and they will in fact split each other. I think this is the end. Yes, it is the end of this lecture. So this is also the end of this chapter. I think it's chapter 2. So what we'll do next lecture, we'll start chapter 3, which is the conformations of our molecules. So you can start reading up on that. Yeah, so in the meantime, continue studying hard, and if there are any questions, just send me an email. Okay?